Welcome. Let me say something about delta sets. They have been introduced in the 50s by Eilenberg and Zilber. Zilber, very unusual mathematician because he made his PhD here in '63 when he was 40 years old with Gleason, Andrew Gleason and Raoul Bott. I'm a big fan, or became a big fan of delta sets, first of all because they are so general. They are much more general than simplicial complexes. They are also more general than simplicial sets, a misconception which you see often in the literature. Simplicial sets have more structure, so they are less general. It's also easier to understand delta sets than simplicial sets, in my opinion, because they have less structure. So they are just these face maps which satisfy some compatibility, which gives you then cohomology. Equivalently, we have a Dirac operator. I like the data structure of Dirac matrix because this is just an n times n matrix. This is a set with n elements, an n times n matrix. And you have also something which tells you what the dimension of each element is. So that's a very simple to implement in a computer, actually not more complex than a simplicial complex. And simplicial complex are the simplest object. They have only one axiom. Even simpler than graphs. Graphs always define you simplicial complex, the Whitney complex, and so also a delta set. Now graphs are very intuitive, and I still like graphs, and also for every delta set you can immediately get a graph by just taking the vertex set here and connect two if one is contained in the other. And this Dirac operator or these face maps equivalently tell you when something is contained in something else. So here's a very simple delta set which is not a simplicial complex. It's an open set in a simplicial complex. I like this kite graph, has appeared quite a few times in my work, and it's just a tripartite graph, K112, and so this is a very nice graph, and you can look at the open set of the edge, or any simplex has an open set. The Alexandrov topology is defined by the stars, and this is an example of a star. And what you have is you represent it just as a set. In the computer, represent it as a set here of three elements. This is the edge, and these are the two faces, the two facets, the largest dimensional elements. There is no vertex here, right? But what you do, and that's kind of the new thing, you still talk about points, but points are now just the lowest dimensional parts of space. That's what Euclid says, right? A point is something which has no part, and that's what we have here, the lowest dimensional part. This is actually a point here. There's only one point here in this. And then we can also the Dirac operator, that's kind of equivalent to give the face map telling you what is contained into what. Right? That's a face of this triangle, and the d square is the Laplacian, and the kernel of these blocks gives you the Betti numbers, gives you the cohomology. And then you have also the Euler characteristic is just counting, super counting the sets, right? So in this case, what you have is two elements with energy 1, and this has energy -1, so the total energy here is equal to 1. That's the Euler characteristic. And the dimension, what we have here in this case, this would be, has dimension 1, this has dimension 2, this dimension 2, so there's no element of dimension 0. Even so, these are the points here. Now, what is curvature? So, I actually wanted here just to write down a few theorems which hold in delta sets. And one of the reasons why delta sets are very nice is you can do anything you want to do. You can especially prove theorems, and the theorems are ridiculously simple. If you compare that with, you know, Gauss-Bonnet chain, it actually produces your Gauss-Bonnet chain in the case when you have an even dimensional manifold. This is more general and much more easy to prove. So you have theorems, you have all the constructions which you want to have in calculus. For example, if we want to find the graph of a function, in order to find the graph of a function, we talked about this, you need you need a product, right? You need a Cartesian product, and there's a Cartesian product. There are open sets. There are also quotients. You can take any complex and a closed complex, and then you collapse that together to a point, which is then just the one point compactification of the open set. And so, for example, you can generate the n-dimensional sphere with a delta set with two elements. There's a point, there's the compactification of an open set with one element. And so you see kind of then there's either 1 minus 1 or 1 plus 1 is the Euler characteristic. And the Dirac operator would just be a 2 times 2 matrix for this n-dimensional sphere. So very nice. So everything you want to do do in geometry can be done in these delta sets. And this is all thanks to Eilenberg and Zilber from the 50s. Very nice. And more modern approaches to this are kind of from category theory. You see this as a pre-sheaf. But I always found this a little bit forbidding because it, for me, as a almost computer scientist, right? So I like to implement something in the computer. If I can implement something on the computer, it makes sense to me. This doesn't make much sense to me, even so it grows on you once you kind of see how nice and simple it is, kind of from the point of view of abstract nonsense. Then you have actually a very, very, very general structure. And then you can go more general. Of course, you can take the category of sets. You can replace it with another category, and so you have or here this category, replace it with another category, and you get more general pre-sheaves and more general objects. But what you really want to do is geometry. We want to have all the theorem. We want to have Stokes. You want to do physics. I did not mention this. You can do physics very well once you have a Laplacian, because the spectrum of the Laplacian, that tells you something. And you have quantum mechanics when you have a Laplacian. You have electromagnetism when you have this is actually the one form Laplacian plays a big role in electromagnetism, and so on. So you have really nice a nice framework to do geometry. But what I wanted to kind of make a little bit advertisement is about theorems. So first of all, about Gauss-Bonnet. Gauss-Bonnet is a prototype theorem in differential geometry. When you have an object like a surface, what you have is you have parts of space which have positive curvature and parts of space which have negative. The problem with continuum mathematics is that we cannot access the lowest dimensional parts of space, the smallest part of space. We cannot see the edges here, we cannot see the triangles. So we have to use sheaf theoretical methods to access things like curvature. And so we have to define tensors, you have to do all kind of gymnastics to actually define curvature. And if you have a 4 manifold or 6 manifold or so, I implemented all this curvature, the Gauss-Bonnet Chern curvature, and I tried to calculate it and integrate it over a manifold. It's difficult even with a computer algebra system. It's very hard. Here in this case what you do is you just take the point of view that Euler characteristic is the total energy of all the parts of space. So even dimensional parts count positive energy 1, negative dimensional parts have energy -1. So this is a counting thing. And then what you do is you take all these energies and you let them sink to the lowest dimensional parts, to the points. This doesn't have to be 0 dimensional parts. In this case, you would actually have all the energy, which is, in this case, the energy is 1, 1, -1. You have a -1 energy here, and you let the plus energy go to this lowest dimensional part. It cannot sink lower because there is no 0 dimensional part. It has to stick here, and then you add them all together, and what you get is, in this case, the curvature is 1 here, and everything else is 0. If you take a delta set of a sphere, the smallest delta set has 2 elements. So the curvature is all located on the 0 dimensional part and the highest dimensional part. And it depends on whether they have the same sign, and the Euler characteristic is 2. If they have different signs, the Euler characteristic is 0. So that's why a odd dimensional sphere has Euler characteristic 0. Now for odd dimensional manifolds, that's what I started with. All this started kind of with maybe 12 years ago with observing that this curvature here is always 0 for odd-dimensional manifolds. And then I kind of started to think about it for years, and the key to see why this is true is Poincare-Hopf. You can see curvature as an expectation of indices. And that's also the link to the continuum, because in the continuum you can look at kind of Morse functions. You take Morse functions and then you have indices, and the expectation of all these simplices is curvature. So you can do that here, right? You can see what is the average. You have lots of negative indices here, you have lots of positive indices here if you take a random Morse function. So you can take probability spaces of Morse functions. Here in the finite we can take all vector fields. So the vector field is nothing else than attaching to every unit of space, attach a point. You just kind of tell which point, so where is that here? So you just want to have fx, the point, to be in x. And what happens then if you take the energy of that cell and you just put it to that point, then that's what you get is the Poincare-Hopf index. These are indices, are integers, they are divisors, so they are integer value. And so if you take the expectation of these divisors, you get curvature. That's what I also kind of started very early on, kind of and once you see that, you see also that an odd-dimensional manifold, for example, is flat, has 0 curvature everywhere. A circle, for example, is flat if it is not embedded. I mean, if you embed a space into another space, that's another curvature. That's not the curvature. The intrinsic curvature should be, defined, by only looking at the geometry of the space itself. And then another thing, which is kind of something I've thought for quite a while here. I mean, I proved it in 2021. It's still a nice result, I think. If you look in the category of graphs, there is a nice Cartesian product in some sense, not the categorical Cartesian product that's completely useless, but you take the Shannon product. The Shannon product is a very nice product which produces you from and it's homotopic to this. So from a homotopic point of view, it's the same. So it works very well. It has a Kunet formula. You have a Kunet is very important for the homology. It has to work very nicely together. And from the point of view of curvature, it's also behaving nicely. That's what you know in the continuum, right? If you take the product of two spaces, like the product of two spheres, that's a four manifold, then the curvature should be kind of just a product. And what happens is if you just look at it and split it up, you see that the curvature as defined here is also not behaving nicely. For example, this implies, for example, together with Gauss-Bonnet, that the product manifold has a product of Euler characteristics, it's just a product. So maybe I'll say something more about this next time, but that's it for today.